All right, hi all, welcome. Thank you so much for being here. I'm Rachel LaDue. I work for Collins Aerospace in business development, and my passion is getting humans out into space. And you're all here, so I suspect that you share that. It is my incredible honor to have these amazing panelists here today to speak to you. They have contributed already to some amazing missions and are contributing to the development of future missions and enabling things like longer duration and eventually stay on Mars. So I will very, very briefly introduce them with their titles, then I'll give them the mic for 10 minutes each. They'll kind of talk about what they do, their companies, and then after that, we'll talk up here about 30 minutes or so with some prepared Q&A. We tried to anticipate your needs here, but please interrupt. We have a pretty close group here, so feel free. Raise your hand if you have a question. We will have 15 minutes of questions for the audience reserved at the end, so if you prefer to wait, that would be great too. So without further ado, to my left here is Grant Anderson, the illustrious president and CEO and co-founder of Paragon. And then next to him is Anna Kallay. She's the ECLS senior manager at Lockheed Martin. And next to Anna is Phoebe Henson. She's a senior life support systems engineer at Honeywell. So with that, Grant, would you like to kick us off?
Sure, and while they're pulling up my charts, there you go. While they're pulling up my charts, I do want to start off by kind of getting to know the audience. How many people know what a life support system really entails? Yeah, about half the audience. Okay, now here's a more basic question. How many people have left their hotel this morning and worried about having enough oxygen to make it through the day? Well, unless you're a smoker, you probably can say, no, I didn't worry about that. So what I'm going to do first, for one thing, I'm not, the difference between a billion-dollar company and a non-billion-dollar company is I don't have a nice little fancy video going on. But my first chart is going to be just a little history of Paragon. I'm assuming they're bringing it up here soon. But long or short of it is Paragon actually turned 30 years old last week. So we were founded in May of 1993 for the sole purpose of doing life support in extreme environments. Space being the ultimate extreme environment means we do a lot of space stuff, but we've also done ground systems, Navy diving systems, mine refuge systems, some things having to do with CBRN, which is chemical, biological, radiological, and nuclear protection. Really anywhere where if our stuff fails, you die immediately is what we do. Not slowly, but immediately, or very close. So what we do, you can go ahead and bring that up. Look good.
One moment, please.
Okay. So we have been involved in the life support design of every single human spacecraft since about 1999. The Dragon vehicles architecture is ours. We helped Elon start SpaceX back in 2002, 2003. Yay, or my apologies, depending on which side of the fence you're on there. And then also the CTS 100 architecture is also ours. So do I have something to advance the slides with, or do I need to just ask? Go ahead. Yeah, so this is a long history. These slides will be made available, so I'm going to zip through some of them, so don't worry if you didn't get it all. They'll be available to you, or take a picture of it, one of the two. This is all non-proprietary stuff. But as you say, we do both the defense, and the one interesting thing is we do both commercial and non-commercial stuff. We've been involved in the in spacecraft. In fact, we're on the original Orion team that won Orion with Lockheed back in 2004, 5, and 6. And then, but we've also pioneered a few things. The first commercial payload on the space station back in 2001, we broke through all the little barriers of getting all the paperwork done so that, you know, Pizza Hut and Poppin' Mechanics and all those could fly, and Nanoracks for that matter. And also we hold the record for the highest skydive in the world, having built the first operational spacesuit in the United States in 30 years, and skydived Alan Eustace from the tops of space, mainly because we couldn't let an Austrian have the world record. Anyway, let's see, is this going to work?
Next slide.
Next slide. Oh, okay, there we are. So this is so a little bit about. I call ECLS the human, the forgotten subsystem, and I apologize for those in the room who take defense of the male-centric thing here, but it's a fairly iconic picture. And I ask people, I'll go to actually NASA and say, hey, is this the human payload? And they'll say yes. No. Go ahead and click the next click. You will never launch a human in space without a life support system around them. It's a really short, ugly trip and bad for publicity. So very often what you have to do is say, you're going to design a spacecraft for humans, for human exploration. Start with the life support system, because that's really what you're integrating in the spacecraft, not a human, just the life support system. Next slide. This is just classic here. This is, if you don't have an understanding of life support systems, apologize for the little off-color word here, but it is a quote. I'll blame it on Leslie Haas here, my Vice President of Business Development, right? But yeah, there's a bunch of things that are wrong with this, and from a standpoint, you won't really implode if you suddenly get exposed to a vacuum. You essentially embolize and drown in your own fluid in your lungs and everything else. But and the one thing about this, I often get asked, what's the most unrealistic thing about The Martian, the movie, and it's actually how modern the NASA buildings look. Everything else is sort of believable, but that one just isn't. Next slide, please. So we're actually talking about life support from a standpoint of long duration life support on the surface, and in some cases getting to the surface if you're going to Mars. This is not a new thought that ECLS was a problem. This is a quote from George Mueller, if you remember, very famous from the Apollo program, in 1966. And I will say, since he said this, of course, the navigation, communication, I think we've got that pretty far down. We've landed a fair amount of things within a fairly small little oval of uncertainty on the surface of Mars. Obviously, the weight is one thing of getting enough mass down to Mars. Communication's pretty good there, and we're putting more communication assets in. We still haven't proven the life support system. And I will say one thing, I will disagree with the panel that was up this morning when they were saying, oh yeah, life support, we got it to 2033. I think, frankly, 2033 is really optimistic for a life support system to be ready to go to Mars. And I'll maybe explain that a little bit more, or we'll talk about that in the questions. Next, please. So this is the basis of a life support system. It really has 6 elements. The human accommodations, otherwise known very often as crew systems. That's those things that keep you alive. Your clothes and your brushing your teeth and everything else. Will there be clothes required? That's one question. Water management. You've got to provide potable water. It all comes down to a thing about the three. There's 3 things that we worry about. Are this set of 3s. 3 seconds is how long you can survive without pressure. 3 minutes is about how long you survive without oxygen. 3 days worth without water, and about 3 weeks without food. There's also the air management, which is cleaning out the air, what we put out, the CO2 and other trace contaminants. The crew waste management, yes, we're going to pee and poop in space. How are we going to collect that, put it together, refine it, and recycle as much as we possibly can. The food management, which was mentioned by Jancy in the thing before, it is a problem, no question about it. And then the thermal control systems, which are keeping us at the right temperature, because humans are really picky about what temperature they're at. And just remember any battle you've had over your thermostat at home. Next, please. Almost done here. Next chart. Okay, I just wanted to say this is a real simple chart. This is one of you can look up and read. On the right is what's the basic consumptions per person. The kilogram per CM day is kilograms per crew member day. What we need, what we put in, what we take in, what we put out. You're fine to look at that. Then there's the 3-second stuff and the laws of threes. The comfort box we sit in. I do want to hit the chart one more time. You'll see a little red dot come up here. That's where Tucson, Arizona is, which is where I'm from. So I live out of the comfort box all the time. Maybe 3 days of the year we're in the comfort box. So I do want to point that out. And I do point that out to astronauts all the time, selling them their wimps. Next. And then go ahead and click there. So this is a basic idea of a closure chart. This is a derivative of a NASA chart, and it's just all the different things. Again, sort of the visual. If you're more visual than the table we had there. And then go ahead and click again. One of the things you'll notice is closure is an issue. Those are over on the right there. This is a little bit modified, but we have subbattery reactors on space station and stuff, but they all put out a certain amount of waste that gets dumped overboard that you probably shouldn't be doing if you're on a multi-year mission or you're on the surface of another planet. Click again. Also, you'll notice nitrogen just appears out of nowhere here. Mining off of Earth, there's 3 things you're you're going to want to do oxygen, hydrogen, and nitrogen. Nitrogen's really rare anywhere but on Earth, and some of the moons of Jupiter, it's just really hard to get. And then finally on the left there is closure. That's a little bit of, that's a loss of percent per year, and what happens as you go to number of years. I made this chart up for an interstellar life support system graph, but it gives you an idea of how important closure is. To give you an idea, we have trouble hitting 1% per day, let alone 1% per year. And 1%, there was what, 2 pounds per day, essentially the space shuttle leaked, depending on which shuttle it was. Next chart. Oh, and just a little bit more data too there on what the leak rates are right now, value again per day, percent per days. Next. And then finally, some of the things, and we're going to be talking about this, but what is really the issue going tomorrow to anywhere? It's the ORU philosophy is one of the biggest things. We often hear, we hear in the life support world, oh, well, we did this on space station. All we got to do is put those together and go to Mars. Space station was built with 30 minutes of escape to Earth, generally 3 months to replace something critical. You know, you can always manifest it and get it up there. The ORUs on space station are like 100 to 400 pound things. You're not going to replace the whole pump package on the way to Mars or on the surface of Mars. You're going to replace the resistor on the PCB board that went bad. You're going to replace the O-ring in the pump. So the whole spares and maintainability philosophy has to be totally different, and we really haven't started doing that yet. With Collins, they had some things about their modular life support system. Paragon has modular solutions too. But one of the things you got to think about is how are you going to repair something? It really all comes down to when is it going to break? How critical is it going to break? In other words, are you going to die in minutes? Are you going to die in hours? And then, okay, then what are your provisions for repairing it? Do you have a backup so you have something to rely on while you repair it and stuff like that? Anyway, in the medical provisions, somebody else I know talked about that today. Radiation resiliency is a big thing. This whole field hospital type idea of how you're going to run your medical systems, but also what do you do preventively? Do you all give all the women mastectomies before they go because of the prevalence of cancerous tissues in breasts? Or you disqualify those that have the IMB something or other gene, that some women are choosing to have elective mastectomies for to reduce their chance of cancer? And other things, take out your wisdom teeth, your appendix and all that. Psychological problems, again, Jancy mentioned that 30 years ago. It wasn't even on the list of problems to go to Mars. And then the NASA Mir missions happened with the Russians, and it went to number 5 in 1 year because of the issues with that. And I won't get into the issues because there are a lot of PII there. But integrated long-term testing in relevant environments. This is the thing that's missing right now, and this is what makes me a little discouraged about being able to go anywhere in 2033. Is right now there is no way to accelerate a life support test because how they fail are microbial contaminations and deterioration of filters and different systems. You can't speed that up. It's not like an accelerated stress test that you can do on a spacecraft fuselage. You have to wait for them to happen. And oh, by the way, 80% of all of the failures at the ISS have been because of microgravity. So it doesn't matter how well you would have tested on the ground. You didn't know about it until you got up to space. So we need a lot of relevant environmental testing in the relevant environment, which is zero gravity. I prefer around the moon because it also gives that immediacy of, I can always escape out of your brain there. Microgravity is a question. I already talked about that a little bit. Microgravity is also an issue for human survival too. Can we do 1/6 gravity indefinitely? Can we do 0.38, which is Mars? We don't know at this point in time. And then finally, the one last thing that we've been harping on a lot at Paragon is that you do not have mission control after your 5 light seconds from Earth. There is no astronaut I know that will sit there and wait for a klaxon to go off and wait for a 10-second return from mission control saying, oh, go do this. By the time mission control gets back, the astronauts will have switched a whole bunch of switches that are still being transmitted back to Earth. You really do not have mission control. You have mission monitoring at that point. So those are all big things. Next. next. I think that's it. And then all I have again for you, the references, there's a chapter coming out on life support for interstellar travel that I wrote that's coming out in August. The first book is out. I do not make money on these, so this is not a plug like that. And then also I did a winter part talking a little bit on how to choose an astronaut and why we actually go do what we do, which is a justification for exploration. And then a little bit more, and a lot of the things we're going to say today, actually, I also did an ISPCS talk in 2019. And that's it.
Beautiful job.
I think I was there.
Nailed it. All right, while we're getting the charts up, I'll just introduce myself again. I'm Anna Kallay. I'm a senior mechanical engineer at Lockheed Martin. I'm currently working on the Orion program and as a senior manager for the environmental controls and life support team. And for me, it's been a real privilege to be part of that program. It's the first program that I've actually worked from the very beginning, and to see the entire life cycle and all the decisions and the challenges and the issues and the politics and the personalities that influence the outcome. But next slide, please. Tremendous to see everything come to fruition with the successful Artemis I mission last year. And if we get the slide up, you can see there's actually one of the images that was captured during the lunar flyby of the surface. The Orion had external cameras mounted, so it caught quite a few selfies as it was going by the moon. And when I saw those, there you go, there it is. When I saw those first images come across live, it was just breathtaking to see that. Of course, we have another major milestone coming up next year. That's the Artemis II. That'll be the first crewed mission to return to the moon in many decades. And then we also have the next two ships that are in assembly at Kennedy Space Center, waiting their launch dates. I took an interest in space early on as a kid. I grew up during a lot of popular sci-fi production. Some I'm sure you recognize: Star Trek, all the many iterations, and Star Wars. One that really caught my attention, though, I remember watching it the day with my big brother, is the 2001: A Space Odyssey. And it just captured my imagination, the futuristic worlds that were yet to come and to be imagined. And it's probably one of the most well-researched film productions from a technological standpoint. Stanley Kubrick put a lot of time and attention into the detail of the technology. Everybody remembers the gravity wheel and some of those icons. But it's incredible to see all the technology that were just concepts and ideas back then that actually exist today and are more commonplace. And for me, it really sparked my interest in understanding what are the tools and how would you bring those things into being. And so that's why I studied mechanical engineering. Of course, I was also interested in all the other disciplines. And so when I came across the EGLIS, the Forgotten Subsystem, as Grant put it, I was really drawn to it because of its multidisciplinary nature. It just includes everything, including fluids, physics, chemistry, physiology, biology, electronics, firmware, software, control systems, and a squishy human on the other side of that. And
Really squishy.
yeah, it really satisfied my personal goal for continuous learning. And one of the best parts of my job currently is that I get to train new engineers in the discipline and see that same spark ignited in them. Next slide, please. So before I joined the company, Lockheed Martin was already involved with NASA's Mars exploration programs, including the very first Viking 1 lander in the mid-'70s. Since then, Lockheed Martin, in conjunction with NASA Jet Propulsion Laboratory and Goddard Space Flight Center, has delivered half of the 22 spacecraft, including 5 landers and 6 orbiters, that have provided invaluable data about the Martian atmosphere and conditions on the planet. And so we're leveraging that heritage, also working on the Mars sample return mission. I heard that mentioned earlier in the NASA Associate Director's briefing. And that includes multiple systems as well as the ascent vehicle
and the heat shield. We're leveraging all of that experience and heritage as well as the experience operationally and developmentally that we gained on the Orion to develop the next level of advancements for NASA's exploration goals. Next slide. Some of these specific life support technologies, and as Grant put it, life support advancements are key to sustain deep space habitation. So a few of the things that we're doing is not only looking at new technologies, but looking at existing technologies and how we can use them in new ways. And this includes sorbent solutions, trading both liquid and solid solutions, and as well as dust-tolerant mechanisms. The picture on the bottom right is captured by one of the Mars orbiters, and it's a little hard to make out because it's a dust storm. But it shows a storm the size of a continent on the Martian surface. So the surface is very arid and very prone to these very sudden and very violent dust storms, and those will get everywhere, just like we heard from the Apollo crew and their experience on the lunar surface. So we need our mechanisms and our rotating equipment to be able to tolerate that kind of environment and protect them. Cryogenic fluids management, electrolysis, and one of my personal favorites, solid and liquid waste management, because we humans generate a lot of waste, not just in the packaging and other things that we do operationally, but all of the waste that we excrete and perspire and respire. And there's an opportunity there, Grant pointed out, to capture some of that and close that loop and reutilize those waste products. In addition to the life support technologies, we're also looking at the system level and advancing manufacturing techniques to be able to produce hardware and materials sooner and at less cost. In situ resource utilization is another very important area for sustained deep space habitation. The picture on the upper right there shows a crater from a very large impact that occurred on the Martian surface. And the most interesting thing, though, in this enhanced picture are the large boulder-sized chunks of ice that appeared and were ejected from that crater. So that's certainly a material that we want to explore. There's a lot of scientific evidence to show that there's ice underneath the Martian surface that we can harvest and utilize for our sustained presence there. Also, other areas, MEMS technologies, microsensors, and things that we can infuse in our devices, modular architecture. Grant talked a little bit about that and the importance of being able to utilize systems at a lower level and to be able to reconfigure systems easily. Predictive diagnostics is another very important area that we're looking at, as well as reliability of systems. And I captured the statement there from Lakeisha Hawkins. She's the newly appointed deputy manager for the Moon to Mars program office, and she's saying there, I can't read it, but just the further we go, the less and less we'll be able to look back to any capabilities of the home planet in order to help us. And I think that's more true, and it's a very different reality than we've lived in low Earth orbit, and things that we're going to have to do to enable these deep space exploration goals. I think that's my last slide. Thank you.
All right. I think they're going to pull up my slides next. I'll go ahead and get started with introducing myself. My name is Phoebe Henson. I am a senior advanced systems engineer at Honeywell, and I work on life support systems research and development. And you can go ahead and go to the next slide. Great. All right. Honeywell has a very long history of human spaceflight, which not a lot of people know about us outside of this industry, because Honeywell has so many different faces in so many other industries, being a Fortune 100 company. But not many people know outside of this industry that Honeywell has actually been part of every single U.S. human space mission ever. We did We've done life support all the way dating back to Mercury and Apollo. So we've done life support for a very, very long time. And on top of that, we're also part of 80% of all satellite missions. Next slide. And we do a lot of different things on every mission. It's really funny working at Honeywell because sometimes you'll work on a certain program and you'll be like, oh yeah, I'm working like the Orion program, but then there are like 50 different products that you could work on that, and there are so many different teams. So I'm not going to go into all of our different products or our space heritage, but you can take a look at this slide. What we are here to talk about today, though, is our environmental control and life support systems, which is the box in the top right. And once again, that only shows a fraction of what we do. We do a lot of the systems needed for any old life support system, things like cabin pressurization, gas and liquid flow control valves, heat exchangers, pumps, fans, sensors. But then we also do some of the more advanced life support systems that are needed to really keep humans alive in space for long periods of time. We did the LaDue canisters on Apollo. We did Cedra, the zeolite-based CO2 removal system for both ISS and Skylab. And working in research and development, I can't help but plug some of the exciting technologies that we're working on for Mars. That's what I'm going to talk about today. So those new technologies are our Cedral's technology, our carbon dioxide removal by ionic liquid system, and then our new oxygen recovery technology, methane pyrolysis. And you can go to the next slide. Thank you. All right, so Grant really primed me for this. He showed a very, very similar Eclipse diagram. We should really all start to use the same one. I think that would make it a lot easier on our audiences. But this is the ISS Eclipse today, and in yellow you can kind of see two really important pieces. You can see that this Eclipse provides oxygen to the cabin so that the astronauts can breathe, and it also provides CO2 removal. And between those two systems is the carbon dioxide reduction system, which is a Sabatier reactor. And that reactor is essentially the recycling system that helps turn that CO2 that we capture back into oxygen. And that's a really important piece, because the more we recycle, the less launches that we have to do, the less consumables we have. And could you go back 2 slides, actually? Thank you. And that's really important, because the more we recycle, the less consumables we have to bring to Mars. But you'll notice that this ISS Eclipse is currently limited to less than 50% of oxygen recovery from CO2. And the reason for that is because of the limitations of the Sabatier reaction. The Sabatier reaction takes that CO2 that's captured from the cabin, reacts it with hydrogen, and creates methane and water. The water can be sent back to the OGA to be electrolyzed back into oxygen for the astronauts. However, it requires that hydrogen in that Sabatier reaction, and we lose that when we vent the methane overboard. That's the waste product of the Sabatier. So unfortunately, that system is limited to less than 50% oxygen recovery from CO2. Our new technology that we've been working on with NASA for the past several years is our methane pyrolysis technology. Can you go back? Thank you. Is our methane pyrolysis technology, which takes that methane waste product that's currently vented overboard, and it splits it, methane is CH4, splits it into pure hydrogen and pure carbon. And that hydrogen can then be sent back to the Sabatier reactor, where it can then go and produce more water and thereby produce more oxygen. So by adding this methane pyrolysis reactor, we can increase the recovery of oxygen close to from CO2 to close to 100%, which we believe is one of the key technologies that's going to enable us to go to Mars, and not just go to Mars once, but go to stay, because the more recycling technologies that we have, the more consumables we can reduce, and the more likely it is that we can go to Mars and continue to go there mission after mission without it costing too much money, a prohibitive amount of money. And that's really the goal of these new technologies. So you can see with this pyrolysis reaction or net reaction for the entire air revitalization system, is CO2 is turned into oxygen and pure carbon, and that's the ultimate goal for recycling on Mars. Next slide, please. There are some really key advantages that we like to talk about when it comes to methane pyrolysis. I already talked about how we increase our oxygen recovery to nearly 100%. You'll also notice that it leverages the existing Sabatier technology, so there's no new technology we have to go improve. And then the carbon that's produced is deposited onto a substrate, and that carbon is not coming off once it's there, which is a really key concern when it comes to life support systems. Well, what if that carbon, that soot, were to get back into the cabin? That is obviously something we don't want to do, but that is one of the big benefits of this technology, is that you produce this really hard carbon product. And we've also been working with universities and NASA to look at maybe what these resulting carbon bricks could be used for. There's been some talk of maybe using it as building materials on Mars, or things like that. And this is a very robust technology. It's actually been around for a few decades. Honeywell uses it in some other proprietary processes in the industrial and aerospace world. So next slide, please. The other technology that we have been developing is our advanced carbon dioxide removal system, known as CDRLS, the carbon dioxide removal by ionic liquid system. In case you can't tell, it uses an ionic liquid as its CO2 absorbent. And the reason that we picked this liquid is because it's a liquid. It offers the ability to remove CO2 continuously rather in batches like the solid absorbent beds. And that means that you can easily integrate it with downstream systems like the Sabatier reactor and reduce the size of your system dramatically by eliminating a lot of the intermediate equipment. The advantages of CDRLS are the lower CO2 partial pressure, so it can maintain the concentration of CO2 in the cabin to a lower level than the previous technologies. And that is really important because astronauts have complained in the past about headaches and not thinking clearly, and they believe that it's due to the high CO2 levels in the cabin. And when we go to Mars, we need to make sure that our astronauts are performing well. So maintaining a comfortable level of CO2 is very important. In addition, the size, weight, and power of the system is very low, and we also proved last year, and we reported in one of the papers at the International Conference on Environmental Systems, that CDRLS actually removes a number of trace contaminants as well as just CO2. So it can actually take a huge load off of the trace contamination control system that's also part of the ECLS. So we're really looking at this technology for as a provider of multiple functions. As for where we are, we currently have 6 separate ground demonstrations of this technology built and tested. You can see pictures of them there, and you can go to the next slide, please. And we're also in the process of designing our flight demonstration unit for demonstration on the ISS, hopefully, potentially, before the end of ISS. So. As for methane pyrolysis, we're at a similar, status. We I've actually recently delivered one of our prototypes to NASA Marshall Space Flight Center, and they're testing it integrated with a Sabatier reactor sometime soon. So we're really looking forward to the results of those tests. And then we're also in the process of performing our designs of a flight-like reactor so that we could also look at what this would take to put onto ISS and integrate it in microgravity. Both of these technologies have been funded partially by Honeywell, but also partially by NASA, specifically the NASA Exploration Capabilities Life Support Systems Group. That's a mouthful. And so we gratefully acknowledge their help in the development of these two key technologies for Mars. And that's all I have. Thank you.
Awesome. Thank you guys so much. I learned so much about you. Can I do a really quick go back? Anna, you did such a great job in telling us what inspired you and what brought you to this this industry and doing this, keeping humans alive in the future. You were the people doing that today, so that's what fascinates me. So Grant, can you take just a second to tell us why you started this?
Yeah, and Anna, I have a lot of the same thinking. The multidisciplinary nature of having to deal with humans in space. Starting Paragon, one thing that really turned me on about it was that you need to know biology, you need to know chemistry, you need to be a mechanical engineer, electrical engineer. It is such an issue. I mean, I was faced coming out of college. Well, I wanted to work human space flight for sure, and I know before I started Paragon, I was the chief design engineer for the solar arrays for space stations, so the big blue and gold things are my design, but it's the human element that really makes it interesting to me. And I could have designed, robots on the factory floor, and for that matter, a communications and spacecraft is just a robot, but in a really cool place. But when you get the humans in there, the ones that accidentally twist off your knobs and kick your stuff, and your urine in the morning is totally different from your urine in the evening, and so there's all sorts of variables that it keeps getting thrown at you, and so it's just exciting to have to design around all that.
I love that, designing around the person who inevitably trips over the thing you spent $1 million to make. Mm-hmm. Yeah, I agree with that.
John Young used to do that. Doesn't matter, of course. It was his
signature move. Yeah. Perfect. Phoebe, can you give us a second?
Yeah, I definitely feel the exact same way. I feel like everyone who works in life support and ECLIS loves that multidisciplinary aspect of the technologies and of this industry. It was definitely the same for me. Also, there's this part of me that really loves the efficiency of turning waste back into something that you can use again. There's just, I don't know, the engineer in me is just yes, we're using everything we can.
Efficiency, I love it. Great, thank you for accommodating that switch back. I appreciate it. So one of the questions that is on my mind, and going back to what you said, Grant, to start with, we've been on the ISS, we've had 20 years of uninterrupted human habitation. We've gotten good at some things, but in order to go further and help humans go further, we need to, as part of the qualification program, test more in long-term relevant environments. So what are kind of your thoughts on when is testing on ISS enough, and what's the next test bed?
Sort of like doing testing is sort of like doing a proposal. They're never done. You just kind of try to release them to the wild. But obviously we're in a serious business here, and ethically, I don't want to have anybody light the fire to go to Mars without a really, really good feeling in my mind that we've done everything we can to make it work. What needs to be done really is to build the system and start and build the system from the ground up. It's interesting, even with the gateway and stuff we're working on now, one of the primary instructions from NASA was use as much the ISS hardware as you can. Well, ISS hardware wasn't designed for long duration life support. I hate to tell you that. And I think Robin Gaines won't blush if I say that I don't think there's been more than 6 months that something in the life support system hasn't failed on the space station. And that's 6 months times 4 is about how long it's going to take you to get there and back on a good trajectory. So getting it built and getting it out there and maintaining it and playing with it and like I say, you have different humans come and they have different dietary things and frankly, all of our waste products are slightly different. So you've got to really test this whole, again, why we like the variability of a human, and it just can't happen once. The problem I have with the 2033 thing is that means we should be up and testing what's going to be going to Mars now, because it's going to take 3 lifetimes of that trip to figure out all things that might go wrong. So we have the mental assurances to ourselves that say, yea, verily, we're not sending somebody to their death, frankly, which sounds really harsh, and I maybe we get quoted for that, but that's really what's at stake for what we do. How's that work?
I appreciate it. You can go right to doom and gloom. I mean, we can't put as much like pictures of fire when we talk about life support. We don't get that flexibility, so apologize for that. Anna, can you kind of add on to that? What do you think is working well on ISS, and what have we gotten good at?
Yes. Well, let me first start with the International Space Station is certainly a technological triumph. And with the contributions of over 15 nations that came together to support that. And the fact that we've had a sustained human presence for over 2 decades living off the planet is just incredible to think of. And I attribute that to the life support system on ISS for what it is. Of course, there are 2 systems, including one on the U.S. segment that we've talked a lot about today, and also one on the Russian segment, which gives some diversity in the system. We'll talk a little bit about what that means to reliability and maintainability. The ISS life support system, though, it did evolve over time. It had more failures than were originally predicted, but to do that type of testing where you bring out every possible scenario and system on the ground is very expensive and it's time consuming. And so given the proximity to Earth, the ability to affect very relevantly quickly resupply missions, the ISS could tolerate a higher degree of defects than we can for our long-duration missions, where a resupply to a Mars location is anywhere from 8 months to a year away, and the crew can't wait that long. So because it is 3 seconds, right? So to the point that Grant made, some folks might ask, well, but it's there. We've spent a lot of money and time on it and developing it and wrung out a lot of the issues and problems, and we've got a mostly or partially closed loop. So why don't we just replicate those systems and, build another one and send that off to Mars? And there are some merits in that, but there are a lot of things to consider. First of all, the sheer mass and volume of these systems, the power that they require to operate. And also, part obsolescence is a big problem. Parts that were manufactured 10, 15 years ago, those might not be available anymore. A lot of vendors went out of business during the pandemic. So we'd have to do a whole series of part screening to even contemplate that. And just simply the fact that in the past 10 years, 20 years, technology has evolved. We have a lot more capability than we had 10 years ago. And so I think a hybrid approach might be a more pragmatic effort in taking those systems and certainly the technologies and capabilities that have been proven in space and repackaging those and adding, infusing new technologies with more advanced manufacturing techniques so we can bring those to production more quickly. So I would recommend that, certainly we advocate that there is a lot of capability on the space station that we can certainly learn from and leverage. But in order to contemplate putting humans on a planet that takes anywhere from 8 to 12 months to get to. And the fact that a typical, or I guess an average, stay on the planet, Mars journey, would be about 3 years. So that's a very long time for a crew that's going to have a great deal more autonomy than we currently have on ISS.
And part of that autonomy has to be repairability in situ, right? So can you kind of help us understand what the level of redesign is required in designing for repairability versus just trying to make the thing last as long as it could possibly last?
Oh, certainly. Certainly. Well, there's a lot to consider, and certainly in the initial stages of any new architecture, there are a lot of trade-offs besides cost and schedule. There's mass, volume, power, and other things that we consider, including repairability, reliability, and maintainability. And so for those, we rely on probabilistic risk assessments to point out where the areas of our system have vulnerabilities that could cause them to fail at a higher rate than we can tolerate for the system. So we have a couple options that we can use. In that case, one of those includes redundancy, so adding more components of the same, so we have backups. And this is very common. Commercial aircraft fly with triple and quad redundancies in their critical systems, and that gives them a lot more operational flexibility because they can fly with defects as long as they have sufficient redundancy left. Part of the problem, though, in spacecraft is that we have a risk of common cause failures. So if you have a latent defect in a component, then that could wipe out your entire liquid redundancy. So then we look to dissimilarity in other systems. And I gave the example of ISS where you have two completely dissimilar systems to provide the same function. Of course, that's very expensive because you're developing an entirely separate system on different technologies. But one of the other aspects too is maintainability, and I think that's an important tool that we haven't fully factored into our space architectures, because traditionally we don't want to provide a high level of maintainability at the operational level because crew time comes at a premium, and so we don't want them to spend their time with very high intensive maintenance systems. But for a crew that's going to be so far away from the planet, I think we're going to have to rethink how we design for maintainability and reconsider those trade-offs that include mass and cost and schedule, because the crew that is on a planet where mission control is, a 20-minute comm lag away, they're going to need to be able to be more self-sustaining and maintain those systems, and maybe even have the capability to manufacture replacement parts for those systems. So I think for future architectures, a greater degree of maintainability for the crew themselves, and to equip them with all of the training and the equipment that they're going to need to effect those repairs.
Thank you, Grant. Did you want to add to that?
No,
Okay.
go for it.
All right, so thank you very much for that, Anna. What kind of comes up for me after that is if we're now sort of getting into our spacecraft, we're about to launch. We've had a lot of conversations about the psychology of our crew, prepared them, done whatever we need, and we are sort of standing on the shoulder giants with these 20 years of these technologies that we've been talking about, that we've been developing. What do you think is actually a glaring gap? And Phoebe, maybe you can help me with this. What are we just not going to make it to Mars with the technology set that we have today?
I think that we probably could go to Mars now, but I don't think that we want to. I think everyone in this room probably wants to go to Mars and go back or go to stay. And I think that's really what the challenge is there was a recent paper that's coming to mind out of, I believe it was Johnson Space Center, that pointed out all the things that everyone up here already knows, which is that for ISS, the greatest mass going to ISS was for ECLS, the combination of specifically consumables and all of our orbital replacement units. That was the greatest mass. I think it was like 28% or something like that. And so that's a really big chunk of mass and of money. And if we go to Mars, we could probably go, but our astronauts would probably be spending all their time repairing equipment. The spacecraft would be huge to carry all of that extra equipment. And on top of that, there's also the consumable mass. I think that if we want to go, and we really want to go to stay, we need to make sure that we do everything we can to make it cost effective with recycling, and as Anna was talking about, doing everything that we can to make everything more easily repairable and maintainable, and find other ways to increase reliability as well.
Perfect, thank you. And you were just talking about the methane pyrolysis. That seems to me like it's going to close the gap that exists today. Can you just talk a bit more about that?
Yeah, the methane pyrolysis technology will will double the oxygen recovery from CO2 and completely close the oxygen gap, which is going to enable significant mass and therefore cost savings for a mission to Mars. We are in the process of testing multiple brass board units right now, and our goal is to hopefully find a way to test it on ISS before ISS's end of life. And going back to we were talking just now about ISS and what might be missing between that and Mars. And I think that we also have to keep in mind that there might be a gap between when we can, when ISS ends and the start of that next mission, where maybe we don't have the opportunity, or we don't have the opportunity, at least directly after ISS, to demonstrate new technologies that could really help with the mission to Mars in microgravity before its end of life. So that, of course, there are many companies trying to solve that as well with the commercial LEO destinations, companies like Blue Origin and Aerospace and NanoRacks and, oh my gosh, I'm forgetting a big one. Axiom, thank you. Yes. So, yes, I think that there's also that concern that we have of, well, what if we don't get the opportunity to test this really key technology before that ISS's end of life? Are we going to take that risk and put it on a Mars mission? Or are we going to bring a bunch of oxygen with us in a bunch of tanks? Are we going to do both? So something to think about.
Thank you. You just struck a chord. So, Grant, you mentioned that you had just fielded something that helped close some of the water gap. Can you talk about that?
Yeah, so the up on the space station right now is something we call BPA, the brine processor assembly. For those who don't know, the urine gets collected and it actually gets reduced down to a brine. Essentially, it goes through a vapor cascade distiller that takes out about 30, I keep hearing different numbers, but 30 to 60% of the water. But that's only 36% of the water. So back in February of 21, we flew up I think it was 21, wasn't it, or 22? When you're 60, all these numbers go. But anyway, so we've closed the gap now to the goals of NASA, which was 98% water recovery. So right now we can take urine from a human and literally come out with a bag of salt, and all the water is back recycled into the system. That's about as good as you can get, because once you get to the hydrous salts that are left over, it's really, really hard to get that out. And by the way, you can't put these salts on your eggs in the morning either. It's pretty disgusting stuff. But what we measure the effectiveness with is actually the pounds consumable, or kilograms actually we do. We're bilingual. Kilograms of your consumable versus the kilograms of water. And right now with the brine processor, because of the restrictions of NASA, it's running about 1 in 33 right now. So we recover about 33 kilograms of water for every kilogram of consumables. We feel we can pick that up to about 150, which is pretty darn good. Right now, I know we've recovered more than 400 kilograms of water, depending on what rate you use for launch costs. That's millions of dollars that NASA have saved just by doing that little closure. And then, so being able to do that with the oxygen and the CO2 is a big thing.
That's awesome. I love it when we talk about it and that ties back to actual dollars that are contributed back to missions to going forward. Anna, would you like to tell us anything about what Lockheed is doing to close this gaps?
Sure. I talked a little bit in the intro about the variety of areas that we're developing. That includes a parallel path of liquid and solid sorbents. We've got 2 systems that are in manufacturing currently and plan to be testing those later this year. We've also got other areas that we're exploring, including at the system level, to address the demand for greater reliability and to reduce the failure probability through part screening, as well as radiation hardening. We may talk about radiation in a bit, but that's a real problem for any long duration mission in space. We haven't seen quite the impact of that on the ISS because we have the proximity, we have the benefit of the planet, and the ISS is about 400 kilometers off the surface of the Earth, so it's not quite in the area past the Van Allen belts where we see the really intense radiation.
Awesome, thank you. So, sounds like in our narrative of what we've done so far, we've closed the loop. We've got a couple of technology gaps that we're closing. Now we're going to put together a crew. So let's, again, kind of zoom out. The point of all of our endeavors and what we came to life support for was to get humans off this planet and to stay as long as possible. And one of the things that we've been really focusing on, and what all of us have sort of mentioned, we're focused on the O2, the respiration, the filtering out all the dust particles and the skin particles, and dealing with the urine and getting water back from that. So we've really kind of talked about chemicals and constituents and closing the loop to make this actually technically possible. But one of the other things that's really fascinating to consider and life support has to help out with is are more of those human factors. How do you help these humans stay safe and sane in this metal tube together where you only have 3 other people to talk to, and there's a lag back to home, et cetera, all these things. So let's take a moment to kind of talk about that situation. So there's 5-6 of us in a metal tube. We're all we have, and we're fixing equipment left and right. What are some of the things that the folks that put us in that spaceship and dreamed of our future, what were they thinking about before they chose us? And Grant, you started in on this when you introduced Paragon, so why don't you take it first? You triggered me one thing because you said 5 or 6 crew, and one of the fights I've had with NASA over the years is don't send an even number of people on any long duration mission. The command structure, unless it's 2, but the command structure of an exploration mission is generally that there is a captain involved, even if I know there's some ex-Navy people here, there's a commander and then there's a first officer and everything else, and you go through certain watches. But when you have an even number of crew, and they showed this in the biosphere out in Tucson, Arizona, the captain ends up
becoming either on one team or another, because it will bifurcate, it will fractionate, we can really develop cliques. So send 2, send 3, send 5, send 7, send 9. Generally, when you get above 20 or so, you can go to an even set, because now you've got a different dynamic. So that's part of it. Also, in references there, I talked about why humanity goes to Mars, and one of the things I felt we had been deficient in selecting astronauts is not looking at the emotional quotient or the emotional capabilities of the astronauts. It was technical capabilities and, the steely-eyed missile person, fighter pilot type mentality. And really, I think the ideal astronaut is your emotional IQ divided by your weight, and that's what you want, is the lightest person with the best emotional IQ on the team.
Love it. Awesome. What about...
Which, by the way, which bias is all towards women, by the way, just so you know that. If you figure it out. Emotional IQ divided by weight, the women are all going to be up on top.
I was going to point out that they only do it up here, but you're representing well. So Phoebe, can you kind of weigh in here? What are some other considerations that we're thinking of? What kind of medical diagnosis? I know Grant mentioned some interventions that we could think of or at least consider, but they're rather severe. So what do you think?
Yeah, first off, I'm all for an all-female crew to Mars. Yeah, that would be awesome. But yeah, as for preventative measures, I think it is something that maybe we need to start talking about. And that I at least don't hear enough is, well, if there's a good chance of a woman getting breast cancer, as Grant mentioned, do you need to perform some kind of surgery to make sure that they don't get that? What other, there are also medications that women can take to kind of decrease those hormones and therefore the risk of getting breast cancer. Maybe that's an alternative option. But I think that a mission to Mars is going to be probably around 3 years, right? So that is a really long time for something where something could go terribly wrong. What if you find out within the first 6 months that someone does have a cancer? Well, you can't really turn around. And another thing is the doctor. Are we just going to have one doctor? What if something happens to them or they need to operate on themselves? That would be pretty terrible. So I think that there was, one of our audience members was saying that there was a doctor in Antarctica that got breast cancer. Did they have to operate on themselves, or were they able to get back in time?
Evacuated out.
Evacuated. Oh, appendicitis. Oh my gosh. Perform surgery on themselves. Wow. That's a cruel world. But yeah, definitely a lot of things that we need to start thinking about. Maybe as life support systems engineers, that's something we need to start talking and thinking about more as well. So.
Right, and a lot of this talk of cancer obviously has been on the duration, the approach that we take. Anna, can you talk a little bit more? I think you have quite a specific perception on the radiation topic.
Yes, radiation is a very serious concern for any long-duration mission. Basically, there are 2 types of radiation that the crew would experience in deep space. That includes solar radiation, which is directional, and cosmic radiation, which is omnidirectional. And the cosmic radiation is probably the worst of the 2. Particles emitted from exploding supernova that include heavy ionized nuclei that can penetrate a ship's hull and directly into human tissue and cause all kinds of terrible things, cell disruption, as well as disrupting DNA functions. And so the ability to protect our crew from that on a very long mission, 3 years, very long time to be out in space. We thought about that on the Orion ship. We brought in, early in the development of the crew module, we brought in radiation experts, and they used tools to analyze the configuration and point out to us areas of vulnerabilities that we could then correct early on in the architecture development. Bart on this one also flew a simulated torso that was instrumented to collect radiation data, to look at the effects of radiation on vital organs in the human system. And NASA's done a lot of studies, including all of the orbiter missions that collected data about radiation on the planet's surface. The Martian atmosphere is extremely thin, so there's almost no protection. It doesn't have a magnetic field like Earth does to deflect a lot of those radiation particles. And so a crew on the planetary surface or even in orbit is going to have a full load of radiation, probably anywhere from 2.5 to 3 times what the ISS crew would typically see. So all of our future spacecraft and habitats as well on the planet's surface will have to take into account some type of measures and countermeasures to protect the crew and shield them. There's some concepts for planetary surface habitats that include building shelters underground, as well as inflatables on the surface that might have sintered bricks made from the soil that are available. But one of the things that we absolutely must take into account is the hazard that radiation proposes and whether that is in the case of preventive medical procedures or even pharmaceuticals. The risk to the crew at this time is very great.
Yeah, thank you. There's a lot to think about there. Realize I have reading to catch up on. So let's land our ship. So we have 4 very intelligent, emotionally intelligent women, in addition to intelligent women, landing on Mars. There's 7 of them, let's say. It's quite a large crew. So we've made
More
it.
the better.
Yeah. We have maybe 2 doctors. What's our day like, day 1, and then day, 40? What are some of those normal routines that you would expect? Anna, do you have a clear picture of what that looks like?
Well, it depends. If you're at the beginning of that journey, you're going to be very busy. Human needs haven't changed much over the millennia, and I don't expect them to change too much in the future. Air, water, food, shelter, all those things are going to be important. And just like early explorers and settlers, they brought what they could with them at the beginning, with the realization that there may not be supplies and provisions for them when they get there. Well, we already know there won't be those provisions in place. So if you're on the early crew, you're going to be extremely busy setting up those capabilities for the subsequent crew to arrive. Now, if you're lucky enough to be on the crew that arrives when all of those that infrastructure is in place, there'll be a more routine set of daily activities. And I would expect that, your morning might look like you check in with the crew commander, do a check-in with mission control, talk about health and status of the crew, as well as all of the instruments and systems on the ship or the habitat. And then afterward, one of you might be assigned to prepare a meal. I would expect you'll dine together, and then someone will be assigned to clean up. And this is the kind of task that the crew will switch on. They'll share, everybody will pitch in and do their part. Then there's also inspections, diagnostics, maintenance to run on all of the systems, inside and outside of the habitat. So if you have to go outside, you'll have to don your pressure suit that'll provide you with all of the breathable air as well as thermal conditioning and protect you from the environment while you do those things. When you come back in, it's probably lunchtime or dinner time. You'll do the same, the preparation and the cleanup for the meals. And then at some point in that schedule, you'll have to do a daily round of exercise, both aerobic and cardiovascular, to maintain the health of your systems. And Then eventually you get around to having some downtime for R&R. But I'll point out that I didn't start off the day with a shower. I know that all of us are used to those conveniences on Earth, but as Phoebe and Grant pointed out, water is a very precious commodity in space, and it's also very heavy and very expensive to transport. So until we have an in-situ resource capability to provide those water systems, hygiene is going to be very different on the Mars surface and habitat than in what we know about it. But as you wind out your day, you're going to have some relaxation time. You might have time to check emails and communicate with your loved ones, albeit with a 20-minute delay either way. And also maybe read or whatever it is that you like. And you'll have a scheduled sleep time as well, most likely 8 hours. And I wish someone would schedule me for 8 hours of sleep. But the day will be very busy. Boredom will not be in your schedule. And you'll be on the greatest adventure anyone's ever known.
Yeah, perfect way to end. Oh my gosh. Thank you guys. This is an amazing panel. I appreciate you. It looks like we have some questions, and I apologize. We were waiting for a yellow cue to tell me to round us out. I'm so sorry. Please go ahead.
Yeah, no worries. Sorry, I didn't want to be rude, but I was looking at the clock, and we are supposed to end in a minute. But I really wanted to get this question in. So I'm Arttu Luganen with Solar Foods. I have a rhetorical argument to make. The oxygen is generated from water by electrolyzers, split into O2 and H2. Everybody's talking about O2 recovery. Should we really be talking about water recovery? So basically what happens is the H2 now, which gets vented either as a form of methane to space, it means that you have no longer that water available. And this is the reason why the ISS, despite this 98% recycling rate, which is fantastic, is still losing water because of the hydrogen loss. So that's my first question. My second one is, and I know I have a background in physics, and I've done lots of systems engineering, so I'm brave enough to ask this question with this background, which is that already in the 60s, people started looking at biological systems for bioregenerative systems. For instance, there are bacteria out there that love to eat hydrogen to produce metabolism that eats in CO2, kicks the oxygen out, and you get something useful out of it. So do you have any opinion? It was in the 60s, but we have never seen anything flying or being in practice in trials. So what do you think is the reason for that? Thank you.
Yeah, actually, the chapter of the book I wrote on
the chapter of the book I wrote on interstellar life support says your life support system will look a lot more like a brewery and a lot less like a farm. One of the reasons you haven't seen that is what we call a balance of plant problem, is that when you are raising biological items, creatures or whatever, there is a lot of infrastructure that goes to look at a brewery, and by the time you start factoring all that in, and then the pathological organisms that can really mess up your bacteria and stuff like that, you end up with a very questionable on the reliability side of it all. I do agree, though, that there's genetic engineering you can do to microbes, algae, things. Actually, when people ask me what's the first plant could grow on Mars, I always say algae and yeast, hoping they don't understand that algae and yeast aren't plants. But they are biological creatures. And I do believe that's, and we've done some studies, you can find one from the Mars one, that you're transitioning over to the biological side you can do once you get on a planet surface. You can't do it in zero gravity, because the zero gravity, the handling of the liquids, the handling of all of the stuff to grow a plant, even hydroponically or aerophonically, just totally outweighs the physiochemical systems, which are going to be more reliable. Nothing's worse than finding a spot on a plant that your life depends upon. As far as a little, fungal spot, you go nuts. Psychologically, it would kill you. But.
All right, thank you very much.
Thanks for the question. Next.
In the interest of time, I won't ask a question. I'll just make a suggestion, and that is it would be good to have a lifeboat on a trip to Mars and back, because it lasts about 3 years and doesn't land on Mars. And it's a long time to spend on one ship. Think about Apollo 13, only a couple of days out, and they had a problem. A lifeboat would, a totally independent ecosystem would provide a way of surviving the crew. If anything goes wrong, you don't know what's going to go wrong for 3 years. So consider that.
Like it. Lifeboat. Check.
Yeah, lifeboat or just redundant systems within the same shell also would do it.
Second spacecraft would be
He's
nice.
suggesting, yeah. Space great.
Hello, thank you so much for taking my question. Grant, you've mentioned previously that there are 6 elements to human habitation, which are human accommodations, water management, air management, crew waste management, food management, and temperature management. There's been a lot discussed in particular with regard to crew waste management and general waste management that comes with space industry endeavors to include issues as large and ongoing as space debris and as nuanced as bags of frozen excrement being left behind on potential planets. I believe it was Mark Martin, who's an assistant professor of biology at University of Puget Sound in Tacoma, Washington, that said there may even be contaminants of gut bacteria from bags of astronaut poo left behind on the moon, which falls under a planetary protection kind of area. Anyway, certainly one area where we have failed, or is at least a point of contention on our blue planet, is related to proper waste management. What kind of considerations, and it's just a general question, are being taken to properly recycle and utilize waste that's left over so that we don't end up with landfills on the red planet or repeating ongoing waste management problems that we currently have here on Earth?
So you're specifically talking about previous waste that was deposited, and
So when we
what
go
would
to
do with that?
when we go to either the moon or Mars, what are we doing about just leaving waste behind?
Well-
so we're not. Are we going to end up in the future with landfills on Mars? Is what I'm
Right.
asking.
No, that's an excellent question. I mentioned in the intro that we create a lot of waste as humans, and it's a concern because it's not a matter that we could return with us to Earth, because we have limitations on the mass that we can land based on the type of systems that assist that landing. So I agree. I think that's part of a concern that we need to think about, and certainly being able to consider that in the materials that we send, and to make those reusable for multiple purposes and not just for a single use, and then we end up with a lot of electronics that are broken and can't be repaired. So those are things that we definitely need to consider in the architecture of the system, and how we would handle those waste product streams if we're not recapturing those and regenerating them into useful products.
Thank you.
That was directed towards me a little bit, but there is a company called... No, I really wanted you to answer. No, okay, yeah, well, you said my name, but I wanted Anna to have a chance at that first. I mean, the one thing is, we will produce waste. There will be a waste farm on Mars. I mean, every single human settlement in the world, but frankly, every single living settlement, there's a waste farm associated with the bacteria. And in fact, bacteria sitting in zero gravity, they tend to not metabolize well because those wastes build up around them as opposed to them dropping through the column. Everything's leaving waste. Anything that's producing energy or reducing energy to useful stuff. The matter is making it acceptable. Now, the question of acceptable is the newer thing, and that's more philosophical. You also mentioned micrometeorite and stuff. To me, that is a subset of, because pressure control is life support, so trying to figure out how to make sure micrometeorites don't pierce you is part of that eclipse problem. And Paragon does have a solution, by the way. So.
Yeah, so related to the waste, I mean, is the model the Grand Canyon where you have to take everything out with you, or is it Antarctica or the Himalaya where it kind of stays there? But my question is related to waste, but on a 36-month mission, is NASA planning for the astronauts to wear this same pair of underwear for a month, turn them inside out, And, essentially, each person carries 18 pair of underwear, or, let them go 2 months and, 36 months, 18 pair, you wear them, 2 weeks one side. Or is there a thought to, disinfect them and clean them somehow, or use the material to, manufacture them out of some sort of biodegradable material, but then you still have to, pack additional pair. And then coupled with that, when you recycle waste, there's, paper, there's hygiene products and so forth that go along with that. So I guess that's part of is this part of Eccles? I mean, undergarments, or, where does that fit in with things? And is there a plan for that now? I mean, obviously that would have to be a contract.
I can tell you that that's been a major topic of discussion on not specifically the clothing, but on the Orion manifest. So as I mentioned, the Orion ship is mass limited, both for the launch vehicle as well as for the landed mass that the parachutes can sustain. So that's a question that we had to take into consideration. So we provided the capability to NASA to maintain, X amount of pounds on the ship aside from the equipment. And I don't regularly sit in, but I have been in some of the discussions where they talk about these trades, and some of the trades that came up were crew clothing, and reducing the amount of clothing is a trade-off or something else that they want. I think there's a lot of opportunity, though, in the technology development of new textiles and materials that we could build clothing out. They're already clothing, mostly athletic wear, that can wick perspiration away from the human body. But I think that's another viable area that could certainly help, not only in the amount of clothing that we have to bring, but if we can reduce that even by half, that would be a substantial mass savings.
You still need a washing machine, though, even if you have advanced materials.
Well, again, it goes back to how much water can you use? How much water can you allocate for drinking versus laundry? So those are economies. But once we get the water production system on board the planet, then we'll be in a much better condition. But hopefully by then we've gotten better at textile manufacturing.
And there's a joke that goes well with this, of course, which is the Army guy that goes up and says, "Hey, men, we have a good news and bad news. The good news is we all get a change of underwear today, and the bad news is, Pete, you change with John. John, you change with..." Right? So, but you may have noticed in the beginning, I kind of didn't decide if we use clothes at all. There's a psychological aspect, obviously, a social mores aspect of it. But one of the things that very often gets is, well, this concept of just, everybody knows each other, so they don't wear clothes at all. The problem with that is that actually some of the various waist areas tend to be the lower portion of the body, all the hair and stuff. The underwear actually keeps that from floating around all over the place. So it's not necessarily the best thing to have no clothes. And then all of the moral and mores aside on that. But the main thing is low lint. One of the biggest things is getting rid of the lint. If you clean out a filter on the space station, it's hair follicles, hair, and lint are the three big things. And I think lint is usually used to be the biggest until they really started controlling the clothes.
So just to, I found the reference that I was thinking of, but it's there's a Nature Scientific Reports number 5950 from this year. Effects of body size and countermeasure exercise on estimates of life support resources during all-female crewed exploration missions, and by the European Space Agency, plugging my agency. And they concluded it's not for an equivalent crew number of women who are the same size as males. Female physiology is a little bit more efficient, so actually even then, even if the women are same stature as males, it's a more efficient crew energetically. So there you go, science in nature.
Okay, so our all-women mission is somehow not very close.
For those of you who do human factors, we measure. For those of you who do human factors, we measure in percentiles, and then there's generally this 5th percentile Japanese female, which doesn't mean they have to be Japanese, but it's that stature of that to a 95th percentile American male, because we tend to be biggest except for the Dutch, if you want to do. And the ideal, it seems like the ideal crew is 5th percentile Japanese females all going to Mars. So that's way it goes.
So I can't say what we're all thinking, but this has turned into a really fascinating narrative in which we sent all women in various states of clothing.
I love it.
Thank you so much for coming. Appreciate your